Let's look at the review for 1.2, 1.3. We're going to start off with limits from a graphical perspective. So part A, we want to find the limit of this g of x function as x approaches -7. In order for a limit to exist, remember that the graph has to approach the same real number y value from both sides of the target x. So we want to approach -7 from both sides of -7. So I'm going to choose a value relatively close to -7. So slightly to the left of -7, I'm going to pick a point here. Slightly to the right of -7, I'll pick a point on the graph. And I'm going to follow the path of the graph towards -7. And we see that they're both moving us towards -infinity. Now, there's consistency from both sides, but it's not a real number. So we'll say the limit doesn't exist, D and E. And then in parentheses, we'll say, well, there within does not exist. We can give a visual representation that the graph is approaching infinity, positive infinity from both sides of -7, but it does fall under the does not exist category. Okay, g of -7, we just want to pinpoint, does the graph exist at -7? So -7, we see there is a point defined, and that point is at y value of 5. Limit as x approaches -4. So let's find -4. -4 is here. We're going to pick a point to the left of -4 and pick a point to the right of -4. So I'm just going to highlight. I want to pick points relatively close. And now I'm going to move towards -4. So as I move towards -4, one is approaching a y value of 2, the other is approaching a y value of -2, and we see that there's no consistent path or movement towards the same y value, so therefore this limit does not exist. Okay, g of -4. G of -4, we want to pinpoint the graph at -4, so at -4, we see there's a hole there, but the graph does exist at this point here, so -2. Limit as x approaches 1 of g of x. So I want to approach 1. I want to find 1 first of all, and I'm going to pick points on either side of the path. And I'm going to move towards 1. And if you move towards 1, you see that I have both arrows moving towards the same y value. That is enough for a limit to exist. Even though the point is a different location, the path is consistently moving towards the same y value. So therefore, the limit exists at -5. G of 1. So this is where we see a distinction between limit and order pair, right? With limit, we're looking at the consistency from the path. For g of 1, we just want to know where the point is. So there's a hole there. There's no point defined, but there's defined at 3. G of 6, again, we just want to know where that order pair is. So g of 6, even though it's not highlighted, it is a point. So that is at -1. Sorry, -2. That's -1 there, -2. Limit as x approaches positive 6. So I'll pick a point to the left of 6. I'll pick a point to the right of 6. I'll move towards 6. And we see that they're both moving towards a y value of -2. So look at the distinction here. E and F, and then look at G and H. So E and F, we see that there's a hole in the graph. If there's a break in the graph, we know that your limit and order pair are not going to give you the same value. And we see that here. However, look at what's happening at 6. At 6, there's no break in the graph. The graph is continuous, right? There's no hole, there's no asymptote, there's no disconnected parts. So when you have a continuous function, then you're not going to get any distinction between order pair and limit, because the point is going to exist. It's going to match the path of the graph from both sides. So we're gonna, next section, we're gonna talk about this concept of continuity and just a little bit of a preview. Order pair and limit, if they give you the same y value, that's an indication that we have a graph that is continuous, no breaks, no holes, no gaps. Okay. All right, so the more challenging part of graphing is where we have a list of properties and we want to translate this onto a graph. And the reason why it's more difficult is because there is variety in terms of how students may be able to represent. So basically, there are different ways that you can sketch a graph and still be correct in certain instances. But also the fact that there's a couple of things we have to keep track of, and sometimes it's harder to create a graph rather than just identifying information from a graph. So something that I want us to be able to do is that not just any graph, I want this to be a function. So what I mean by that is whatever we create, it needs to pass the vertical line test. Okay. So the strategy that I'm going to take with these types of with this type of problem is I just want to do the easiest things first. So I'm going to just go ahead and knock out the order pairs. Those are easy, right? So I'll leave the limit for later, but I'm going to take care of the easy ones first. So g of -2 equals -1. That's just an order pair of -2, -1. Okay, I'll go ahead and check that off. G of 2 equals 3, another order pair. Limit, G of 6 equals 7. Okay, so I'll go back to what's happening here. Limit as x approaches -5 is equal to -3. So I want the path of the graph to move towards -3, -5, -3, but I want to leave the option open for maybe there's a hole there. All right, so just like how we saw here, right? When we had limit exists, it could be a hole, it could be an order pair, but I'm going to just leave it as a whole just to kind of give me some options. If I need to fill that in, I can fill that in later. I don't have to erase it. So -5, -3. So I want the graph to move towards that order pair of -5, -3. So I'm going to put a hole there. And I just want the path of the graph to move towards it, but I don't want to complete the graph yet because I want to be able to connect these to where they're supposed to be. So right now I'm just want to just kind of have a starting segment moving towards it because I just want this statement to be true, and then when I have all the pieces kind of set in place, then I can kind of figure out how I want to connect or not connect with the rest of the graph. So right now I'm leaving this as an incomplete, but at least I've taken care of this property here, right? If I pick points on either side of -5 and I follow the graph is moving me towards -3. Okay, g of -5 is undefined. So basically, I don't want anything here to be defined at -5. And I just can basically leave this alone because I have a hole here that matches this property. There's nothing else that will be defined here, so I'm not going to fill in any points. So if I leave that alone, I've taken care of part B. Limit as x approaches -2 is equal to -infinity. So we have to understand that -infinity falls under the does not exist category. And we want this to basically have something like this, where both sides of the graph is moving towards infinity, but instead of positive infinity, we probably want a graph to look more like this, where we want, wherever the asymptote is, we want the graph to fall into that point. Okay. So we have, as we approach -2, so I know that there's a vertical asymptote at -2, so I'll go ahead and drop a dotted line here. Now, it may seem strange that there's a point defined on this asymptote, but the reason why we can do this is because these are all piecewise functions, so we're just tackling, we're just inserting different functions on top of the same graph. As long as it passed the vertical line test, we're okay, so this is still fine. We want the graph to fall to -infinity from both sides of -2. So I'm going to create an incomplete graph here, but at least I want this part to show. I want the graph to kind of fall into that -infinity when we approach -2. Okay, so I don't know what to do with these branches just yet, but at least I've taken care of this and I can figure out how the rest of it works. Okay, limit as x approaches 2 is equal to 3. So I want the graph to connect to 3. So, and we see the order pair is here, so I'm just going to have the graph connect to this point. So this tells us that this is going to be a continuous function, right? So the graph is moving towards the same y value. The order pair is also located at that point. So it's just going to be a, it's going to go right through that point. Okay. And finally, the limit doesn't exist as x approaches 6. So we have a lot of options here. So we have a variety of options. So what I mean by that is there's a lot of ways to show that the limit doesn't exist. Maybe you can make disconnected parts of graph. Or disconnected parts or segments. We can create a vertical asymptote if you want. Technically, that falls under does not exist. And maybe you can just make it an endpoint. So we have a lot of options to create where the limit doesn't exist at 6. So we can make it an endpoint. I can stop here, this is fine, or I could make it where it's different disconnected parts of graph. So as I go towards 6, or I can make it vertical asymptote like how I did over here. So we have, whenever you see limit doesn't exist and you're trying to sketch a graph, you have a variety to choose from, okay? All right, I just want to kind of fill out the rest of the graph here. I have some disconnected part. This is okay, but just to make this a little bit prettier here, I'm going to just take these, connect them as I see fit. And I can, this is fine, but I just want to kind of make this a more connected parts of graph here. Okay, but in the end, we need to just kind of take a step back and make sure that we have, that this is still remains a function. Does it pass the vertical line test? I think the biggest trouble that I see from students is sometimes we have some stray arrows in our picture. So maybe you have a graph and you're trying to do vertical asymptote. So you do this, and then you have arrows on this side, and then over here, let's say at -5, you have a limit that exists, and then so you put arrows on this side. And when I see this, I'm going to follow the path of the arrow. So this arrow looks like it's going to continue and it's going to cross through another graph, and that's going to make it, uh, where it's not going to be a function anymore. Or I'm going to follow the path of this arrow, and I see that, okay, this arrow is going to move in this direction, and it's eventually going to cause an issue with the vertical, not passing the vertical line test. So just be aware of stray arrows on your graph, because that can lead to me interpreting that as a graph that doesn't pass the vertical line test and therefore not a function. Okay.